The Stanley steam car is a fascinating machine, and it's surprisingly uncomplicated when it's fully understood. One of my favorite quotes from George Woodbury's wonderful 1950 book, The Story of a Stanley Steamer, is this one. "My first glimpse into the vitals of a Stanley steamer appalled me by the apparent quantity and complexity. Then the situation became clarified. It was different, wildly different from a conventional automobile, and vastly simpler, much simpler than just the electrical system alone of an internal combustion machine. And compared to today's electronically controlled engines, this difference is even more dramatic. The Stanley is basically a collection of fluid systems. The word fluid in this case includes vapors and gases, and it has very few moving parts. So this is the second of 3 presentations which explain those systems in a new and orderly way. They don't try to show the actual layout of any individual car. Instead, they are stripped-down schematics that show functionality as simply as possible. These presentations are based on the functions in a typical non-condensing Stanley in the collection at Auburn Heights, where I volunteer, our 1914 Model 607. There are some slight differences in older and newer Stanleys, but the basic functionality is always the same. In this presentation, we'll be looking at the movement of water. First, let's take a look at some of the symbols I use, because these are not industry-standard pipefitter symbols for these functions. A red line represents a tube or a pipe, and if there's significant movement of the fluid inside of it, an arrow will show the direction of the flow. These are hand valves. The black line crossing the fluid line shows that they can block the flow at that point. And this is a check valve, which allows fluid to flow only in one direction. In this example, fluid can move from left to right, but it can't move from right to left. So, let's start with the boiler. The Stanley boiler is a drum containing water with hundreds of narrow tubes like these connecting the top and the bottom. In the first of these presentations on steam and cylinder oil, the boiler is described in some detail, as well as the importance of keeping it 2/3 full of water. Check out that presentation for this information. It will be clear that, as we use steam to move the car, we're using water. So, we need to be able to replenish the water in the boiler. We start with a supply tank. Non-condensing Stanleys that don't recycle their exhaust need about a gallon of water to go 1 mile. So the bigger the tank, the fewer stops need to be made to refill. We have to move the water from the tank to the boiler, so we add a pump. This is a plunger pump, not a piston pump, so the plunger doesn't make contact with the inside wall of the pump. The packing, in green here, seals the plunger's movement. When the plunger is pulled outward, it creates suction here and draws fluid in. When it's pushed back in, it creates pressure here and forces fluid out. The pump is connected directly to the engine by a long rod, so whenever the car is in motion, the pump is moving fluid. This pump is sized to move enough water to the boiler to continuously replenish its needs when driving over moderate terrain. We need a line to bring water to the pump, and we need these 2 check valves to make sure that everything moves only in the proper direction. When the pump draws water into itself, we don't want it to draw from its delivery line, so this outlet check will keep that from happening. And when it forces water out, we don't want that to be sent back to the tank. This inlet check will keep that from happening. And we send it to the boiler. The dip tube delivers the water near the bottom. Over time it gets plugged by rust and sediment. There is a cap here at the top so that it can be periodically drilled out. Now, recall that the pump is continuously moving fluid whenever the car is moving. If the boiler water level is high enough, we don't want any more water to go in. So we add this bypass line, which allows all the water that's pumped to flow back to the tank. Of course, we need to be able to choose whether the water returns to the tank or is forced into the boiler, so we need this bypass valve. When it's closed, all the water that's pumped has to go into the boiler. That's fine, but when we open it, because we want to bypass the feed water, we don't want the pressure here to start pushing boiler water over into the tank. So we add a check valve right here. Problem solved. Now there are times when we need an extra boost of water. Perhaps an operator error allowed the boiler level to get too low, or the terrain might be hilly. So we add a second pump, doubling the pumping capacity. These 2 pumps are distinguished by their relative locations in the car. That first one is called the front pump, and this one is the rear pump. We'll add a suction line for this pump, the same two check valves for the same reasons, and connect its output to the delivery line. But if you recall, the front pump by itself is a pretty good match for water consumption on moderate terrain. If both pumps delivered all the time, we'd have to twiddle the main bypass more often, switching between feeding too much water and not feeding any at all. So we add an independent bypass line just for the rear pump. As usual, we need to close off this bypass line when we want to force the rear pump's water into the boiler. So we add the rear bypass valve. Now we have another one of those situations when opening a bypass could allow the loss of something we want to keep. In this case, if the rear bypass was open, it would let water from the front pump go through this line back to the tank. So what do we need? Everybody together now. A check valve. Notice here that the rear bypass valve controls only the water from the rear pump. The main bypass valve controls all the water that's being pumped. When it's open, it's bypassing the output from two pumps if the rear bypass is closed, or bypassing the output from only one pump if the rear bypass is open. Now, sometimes you will hear the main bypass valve referred to as the forward bypass or the front bypass. Even the Stanley instruction manuals use this second term, but it is misleading. The rear bypass manages only the rear pump. The one they call the front bypass does not manage only the front pump. So in training sessions with my students, I always refer to this one as the main bypass. So, there's the entire water delivery system of a Stanley. Not too hard to understand, right? Now, we've seen that we need to feed water to the boiler or not to maintain our 2/3 water level inside. But how do we know how much water is in there? The Stanleys couldn't just put a window in the side of the boiler. Not only would its structure have a weak spot, there wasn't any glass at the time that could withstand that pressure. And your window would be under the hood in the dark and hard to see from the driver's seat. To go after this problem, they started by adding a tube called a boiler column, a well-known component of steam boiler systems. Since it's connected to the boiler at the top and the bottom, this tube will have water in it at the same level the boiler does. In relatively low-pressure systems, such as factories and locomotives, a chamber could be put into this column with a narrow, thick glass window. But again, at that time, there was no glass tough enough to take the 550 psi of the automobile boiler. So the Stanley brothers invented a clever thermostatic device, which they called the 3-tube indicator. It is able to reflect boiler water level without creating any weaknesses in areas of boiler pressure. Here is a standpipe with a closed top and a connection to an open-topped glass tube, which is located inside the car where the driver can see it. This little system is completely filled with water, all the way from the glass to the top of the standpipe. In the real car, the glass is actually positioned higher than the standpipe, so water is not inclined to run down out of the standpipe. Next, we weld that standpipe to the side of the boiler column. There isn't any real circulation in the boiler column. While the water in there is the same height as in the boiler, it isn't the same temperature. It cools down because the boiler column is sitting out here in the air. It's pretty warm under the hood, but the temperature of the water-filled part of the boiler column is definitely below 212 degrees. And the standpipe takes on that same temperature. The portion of the column above the water level, containing steam, stays pretty hot. Now, when the water level falls in the boiler, it will fall in the column, and the column starts to get hot further down. This heat transfers into the standpipe and heats the water enough that a little bit of it boils, and a steam bubble forms inside the standpipe. The expanding bubble pushes water through the tube, and the water level in the glass rises. At first glance, it might seem counterintuitive that when the water is high in the glass, it's low in the boiler. But it takes no time at all to get used to this, because what's really going on is that the glass either looks like you want it to, or it looks like you don't want it to, so you have to do something about it. In this case, we don't like to see the water high in the glass like this, so we will close the main bypass and force water into the boiler. If we were impatient, we could close the rear bypass too, and force twice as much water into the boiler. Eventually, the boiler water level will rise back to where we want it. The water level will rise in the column too, and start to cool the standpipe, causing the bubble to start to condense, and the water in the glass to start to fall. As it turns out, it would take a long time for the newly refilled area of the boiler column to cool below 212 degrees by itself, and thus it would take a long time for the bubble to condense and for the water in the glass to accurately show the boiler level again. To shorten this response time, the Stanleys added a welded connection to the water delivery line, which has cool water from the tank continuously moving through it. You can see that this will be true whether water is being forced into the boiler or being bypassed to the tank. The cool water quickly drops the temperature of the water-filled boiler column below 212, and the bubble condenses completely. Now we want to be able to test this system every time we drive, so that we can be confident that it will give us the information we need. To do that, we add an opening to the boiler column below the level of the standpipe, and a valve to close it off. This valve is called the tricock, since it can also inform us about the boiler's water level at that height. To test the 3-tube indicator, we open the tricock. Steam pressure here pushes the water down out of the column, heating up the area connected to the standpipe. This simulates a low water condition, and we should see the water rise in the glass. Note that it will not fall back immediately when we close the tricock. We need to get the car moving so that feed water starts moving past the boiler column and cooling it back down. This usually takes less than a quarter of a mile of driving to accomplish. Now, at the end of the day, we would like to force the remaining water out of the bottom of the boiler to scour out rust and deposits that have started forming on the bottom. This process is called the blowdown. We add an outlet line to the bottom and a valve to close it off. In order to scour more completely, we add a second blowdown line at a different spot on the bottom of the boiler and a valve to close it off. And there's one last little piece in this area. If the boiler is empty at the beginning of the day, we need to fill it by connecting a garden hose. So we add a threaded connector to the end of one of the blowdown lines. Finally, there's a component that's a little hard to show on this diagram. The Stanley turns out to be a really inefficient machine. You burn a lot of fuel to make a lot of heat, but much of that energy doesn't help to move the car. The heat from the burner is not completely absorbed here in the boiler tubes, and quite a bit of it escapes out the top. The energy that does get into the steam is not all used by the engine, and the engine exhaust is still pretty hot. In an effort to recover some of this energy, the feed water line at this point is diverted to run through the engine exhaust pipe and come back again. The water in the line picks up some heat from the exhaust, so the burner doesn't have to use quite as much fuel to heat it up to operating temperature. The FWH here refers to this feed water heater. And here is the entire schematic diagram of the water system. Note that of all these parts, the only ones the driver needs to work during normal operation on the road are the 2 bypass valves. And here's a spoiler alert, later Stanleys even did this water management automatically. This diagram is available for download at the link below. Hope you enjoyed the presentation. Be sure to check out the first one, steam and cylinder oil, if you missed it, and be sure to follow up with the third system, which is main and pilot fuels.